So let's start. So let's first recap what we have taken last time. So we introduced last time the concept of p-in junction, which is two samples, one sample of silicon doped with phosphorus, which is N-type, and another sample which is B-type, doped with boron, for example, atoms, and attaches them somehow to each other. We found that a flow of the majority carriers from the B will flow into the N because N has low concentration of holes. So a diffusion will happen for the holes from B to N. And the same for the electrons from N to P. And we said that under equilibrium condition, which is just, open circuit, when this be in a junction, after some time, this current just disappear. Because we said for each hole that leaves the B type, a negative ion will be created. For each electron that leaves the N type, a positive ion will be created. These positive and negative ions is just like electrodes, which will create electric field or potential voltage, which will cause a drift current. And this drift current is in opposite direction of our diffusion current. So after some time, they just cancel each other. And this is why it's called the equilibrium. We also could derive an equation for this built-in voltage, the built-in potential that just created because of these two electrodes in what's called the depletion region or depletion region, the region that has no current carriers, no holes or electrons, just ions, and ions are static, they can't move. And as you see here from this equation, VBI is just a characteristic of the doping and the material. And of course, the temperature. And we said that, we show that VBI is between 700 millivolt to 800 millivolt. And now it's time to explore other, conditions that B junction can work also, like is a reverse bias condition and forward bias condition. In equilibrium, no connection. There is open circuit. I don't connect any source to the junction. In reverse bias, I will connect the source and I will do the same also for forward bias. But the polarity of this source will change from reverse to forward. In reverse, I will connect it in that way, making the positive terminal of the voltage connected to the N side of the junction, and the positive side and the negative side of the voltage to the B side of the junction. This is reverse because they are reversed. The positive side of the voltage source, of the battery, for example, is closer to the electrons or the negative charge. And the negative side of the source, the V input, the battery, is closer to the positive charge of the holes in the B type. And there are other, other reasons why they call it reverse. So we'll explore it in a minute. For forward, I do the opposite. So the negative will be connected to the N and the positive will be connected to the B. This is just any electric battery, for example, or whatever. Some voltage. Okay, good. So let's explore first the reverse bias, or the B-in junction at reverse bias condition. So basically we have our B-in junction. And we have from equilibrium, just before connecting the battery, we have the positive ions here and the negative ions here. Now I will connect a source or a battery in that way, such that the positive terminal is closer or connected to the N, and the negative terminal is closer or connected to the B. And we can call it V reverse, for example, something like this. So what's going to happen now? Basically, since there is a positive here and a negative on the other side, okay? So this will just, you know, increase the depletion region. For example, before connecting this guy, it was like this. Between only these 2 points. After connecting the V reverse, it will increase, for example, further to this point, this new points. And why is that? Because since there is a majority of electrons here, and there is a positive terminal here, so some electrons will just move toward the positive terminal of the battery and consumed there, absorbed there. And for each electron that leaves the N type, a positive ion will be created. So more positive ions will be created. The same for here. Since we have here holes which are positive, some of them will just attracted by the negative terminal of the battery and absorb it there. And for each hole that leaves the B type, a negative ion will be created. That's why the depletion region will increase. Or widen, become wider. Okay? And this is, and we said that at equilibrium, the current is 0 because of the built-in potential, right? So that will increase the condition, this condition, because you have now more charges. I mean the electrodes, the negative and the positive electrodes that we just imagine the depletion region is just like some 2 electrodes. This condition becomes stronger. So we expect that, you know, if there is no current at equilibrium, then also there is no current at reverse. Except for very, very, very small currents that I will explain in a moment after maybe 5 minutes or something, 10 minutes. Okay. Good. So the current in reverse usually is very small, very small. Okay, and the reverse bias condition is similar to the equilibrium, except that I just increase the conditions that leads to no current in equilibrium. Okay, and of course I widen the depletion region. One particular or very famous application for this is to treat this junction as a capacitor, just like a capacitance. Let's see what happens if I increase, for example, VR. So let's assume, for example, this is this width here at VR1. Let's increase VR1, or let's now make VR1 equal to VR equal to VR2, and VR2 is larger than VR1. What will happen? More and more electrons from the N side will go to the positive terminal, and holes from the P side will go to the negative terminal. So let's change the current rate, for example. So this is at VR2. And this is a new width of the depletion region. So I can control the widths, and actually there are equations that relates these together, but let's just forget about them. I can control the width of the depletion region based on the reverse bias condition, or the reverse voltage that I apply on the junction. So what is the definition? Why this is a capacitor, and why it's actually a variable or variant capacitor? A capacitor is just a plate, conductor, another plate, another conductor, and here we have some insulator. And in material fashion, we call it dielectric material, or just insulator, and that's it. Which, just to forget about this, dielectric material or something. We don't need it. Just insulator. So a conductor, insulator. And that's exactly what we have here. So this area here is a conductor. This area here is a second conductor. And remember, in the depletion region, no charge or current carriers. So it's like insulator. Yes, a material that has positive and negative, but no current can flow through it. And for any capacitor, the capacitance is epsilon, the electric constant or something, multiplied by the area of the conductor, divided by the distance between the two plates. And since in our case, with this junction, I can control the distance between the conductor and the other conductor, which is the depletion region width. So in our case here, this is variable. and it's a function of the reverse bias or the reverse input voltage. That's why this can be changed, and by turn the capacitance will be changed. So this well-known application for the diodes, the BN junction, BN junction in reverse bias condition is called actually Varactor. This is called the Varactor, which is just BN junction, okay, that is controlled using the reverse bias voltage. That's it. Okay. And if we go, more formally, this is called Varactor Diode. Any BN junction is actually called diode. Okay, so now I will list down the equation that relates the diode or Varactor diode to the input voltage. So we have Cj, the junction capacitance, J for junction, equal to Cj naught. I will explain in a moment what is Cj naught, over 1 minus Vr over V naught. I will also explain what is V naught. Okay. So Cj naught is just a constant, okay, and Cj naught is dependent. It's just like the Vt or Vbi or V naught or Vbr. It's dependent on the doping and all such characteristics of the materials that construct this BN junction or this diode. Okay, so Cj naught is actually equal to square root of epsilon silicon, the dielectric constant for silicon, multiplied by the charge of the electron over 2. Then we have here Na, the acceptor doping concentration, Nd, donor concentration, over Na plus Nd, multiplied by 1 over V naught. And what's V naught? This is the built-in potential that we take last time. So this is VBI. So VBI has many symbols. Some guys call it V naught, like in the book, for example. Others call it built-in potential, VBI. I usually just, use it to call it VBI. So I will exchange between the two, but guys, V naught is VBI. And so this is also VBI. And VBI, we just take it last time, it's between 600 millivolt and 700 millivolt. Okay. So we have here a relation that relates the capacitance to the voltage, the applied voltage. And Cj naught, if you see it, it's just a constant. So if you just, fabricate or made a junction, okay, you know what is Na, you know what is Nd, so it's just like a constant. You know epsilon for silicon, and by the way, epsilon is equal to epsilon r, relative, constant, multiplied for silicon, which is around 11 point something, multiplied by epsilon naught, and epsilon is 8.85, multiplied by 10 to the power minus 20. This constant will be given, so don't worry about it. Okay? Good. So we can go down now. If we wanna draw such, very useful equation, So this is V reverse, and this is C junction or CJ. It will be something like this. Okay, and here is CJ naught. Okay, when VR is 0, just plug 0 here in this equation. So this guy will go. So it will be CJ naught over square root of 1, which is 1. And as you see here, it's disproportional. I mean, if you increase VR, of course, it's negative. Okay, because VR is it's a negative, relates to the junction itself. It's a negative because we connect it in a reverse way. So all these values are negative, guys. These values are negative for VR. As you increase VR in negative, in that way, CJ will decrease. And why it's not linear? Because it's in there is a square root, and also it's also in the denominator of this relation. Okay. There is a very interesting example in the book. Okay. So I think it's maybe solved or not, but anyway, I will publish a homework based on that. I will not solve this example, it's very easy, okay? But I will publish a homework for you due to next week, but I will publish it today regarding the Varactor, okay? One very useful application for the Varactor diodes in something called oscillators. Okay. So you guys for example, in the lab, you have something called function generator. Okay. You guys all are aware of this function generator. Somebody here doesn't know about it. So basically, a function generator is just a device in the lab, okay, that you can get waveforms, electric signal waveforms using some certain shapes, like for example, triangular waveform or a square wave signal waveform, or for example, sinusoidal waveform. And they usually can control the frequency, the output frequency of that uniform. And basically, what's inside is oscillator. Something called oscillator. It's just an electrical, circuit that can generate signals. And we can control the frequency. This circuit has capacitor and also has inductor, okay? And we can control the frequency by varying either the value of the inductor or the inductance, or the value of the capacitance or the capacitance. Usually, what's really easy is to change the value of the capacitance, and thanks for the Varactor. By small change using the knob in this function generator, you actually change VR. You are changing this. So the junction is changing. So you are changing the capacitance. So we can change the frequency of the output signal. Okay. So just one little note here. Usually the frequency, okay, the oscillation frequency is equal to 1 over 2 pi square root LC, inductance multiplied by the capacitance. Okay. And this oscillator is based on something called resonance. I don't know if you studied, if you studied such a thing or not, but this is not our, topic here, and we don't even need to study it in detail. So there are other parts here in the circuit, okay, that overall with this essential part will generate for you the signal. Okay, but this is the part that we are interested in. What our interest is lying here. By changing the capacitance of that capacitor, then we can change the output signal. Okay, that's it. So I will publish this homework today. Let's just remove that. So this is our Varactor. Okay. Good. So, yeah, that's all for reverse bias. We'll talk about something else in the future, maybe at the end of this lecture, also about reverse bias. But let's go to more interesting part, which is forward bias. The third condition. So we take equilibrium. We talk about reverse bias now. The last condition, which is reverse bias condition. I'm sorry, forward bias condition. Okay. In forward bias condition, we have the same junction. Okay. We have the same junction, but now I will connect the battery in the opposite way, opposite to reverse. So negative here and positive connected to the B side. Remember what bands, so here we have positive, here we have negative. Remember what in equilibrium, what bands or makes the current go to zero is this built-in voltage here. Okay, which is it's the built-in potential. Okay. So we need something outside. So to continue the current flow, which is B to N, the holes in B to continue to go to N, or the electrons in N to continue to go to B, we need something to to overcome this built-in potential. So let's write this down. To overcome the equilibrium conditions and allow holes to flow from P type to N type and electrons to flow from N type to B type, we need to overcome or counteract VBR or V naught. Okay? And how we do that? We apply external voltage that should be opposite to this guy, to VBR, which is V forward. This guy in here. So this will overcome. So there are two forces now, two electric fields. Okay, two electric fields. One of them in that way. So this electric field, which comes from VF, wanna a current to flow from B to N, And there is still the built-in voltage or the built-in, electric field that want to do the opposite. So if we put a forward voltage with a value enough to overcome, or larger than, we can say, the built-in electric field or the built-in potential, the flow of the holes or electrons will continue. Okay, that's very basic understanding of what's happening. Okay, and actually, after that, just an opposite to the reverse, the depletion region will shrink. It will not be zero; it will just shrink. Okay, and we will have a continuity in current flow, not like equilibrium or reverse bias condition. And actually, there is even an equation that relates the current through the junction with the voltage across the junction. And this equation, which we don't need to go into the details of its, derivation, is ID, the current through the junction or the diode. That's why I call it D here, is equal to I naught, some constant. I will explain in a moment what's I naught, multiplied by E exponential VD, the voltage across the diode or the junction, over VT, which is the built-in, the thermal voltage, KT over Q, 26 millivolt at 300 degree Kelvin, minus 1. Now, after knowing the three conditions, okay, now we have some element, some new device that we just created out of nothing, okay, and this device, okay, have some characteristics when it's open, when it's connected reverse, when it's connected in forward. So we can use such kind, of device in our circuits. So we need a symbol for it, just like a symbol for resistance. Everybody has a symbol. Why not this? So this guy also has a symbol, which is this symbol. Remember, we have two sides, B and N, right? So this symbol says that you have two sides. This is the symbol for B side. This is the symbol for N side. And why it's not symmetrical, Why they are different? Because current can flow from only from one side to the other, not in general case. Okay, so when there is a current, this current will be like, the carriers will move like this. The holes will move in that way, and the current of the holes in the same way of holes. So this will be the current of the holes. And the electrons will move from N to B. But remember, the current the current of electrons in opposite direction to the electron movement. So also the current of the electron in that way. So we have two currents in that way, in the same way, IH and IE in the same way. And both are in that way. So let's continue the current. So the current is moving from P to N, from P to N, from P to N. So we made a symbol of N just like a wall to say that we cannot have current moving in that way. That's wrong. So let's just remove it. And we made the symbol for B just like an arrow head to show that the current can move in that way. So this is ID, and the voltage just in opposite, just like any other element, the voltage has the direction opposite to the current. For any element except the battery, the voltage and the current are opposite. We know how the current flows. So the voltage drop, VD, across any diode has a direction from N to P. But the current can only flows from P to N. Except in one condition that I will, show you just maybe in 10 minutes. Good. And that's the equation that controls or shows the relation between ID and VD. And basically, it's not linear. It's a non-linear relation. And Ohm's law doesn't hold with that guy. Ohm's law only for resistors, which is linear. ID is equal to VD over R. But here it's not. Okay. Now some observations about I naught. Yes. I naught sometimes called IS. That's very fine. Okay. You will find, and I will explain in a moment why it's called IS. Why we can call it IS. So again, I naught, IS, whatever, that's fine. Okay. If we look at the equation, okay, the equation tells you nothing about the device itself. So let's write it again. ID equal to I naught E VD VT minus 1. First of all, this guy just like any other current is an ampere. Okay. So ampere should be equal to something in amperes also, right? But this term in here is dimensionless. Why? Basically, one is constant, is dimensionless, and the exponent always, forever. If you want to check on yourself, on your equation, the exponent of the E, the natural number E, must be dimensionless. And this is, yes, dimensionless, because V in voltage, VT is also voltage. So all that term is dimensionless. So the only thing on the right-hand side that, behave like a current is I naught. And I naught, yes, has the dimensions of amperes. Another observation here is that VD doesn't tell you anything about the device itself. You can't know if it's silicon, germanium, or whatever, This is just a voltage drop. When the current flows in the diode, there will be a voltage drop, just like the resistor. And VT is just KT over Q. So it's also constant, doesn't relate to the device. So where is the doping, the material, the geometry and stuff? All these lies in I naught, lie in I naught. So I naught actually is function of the geometry of the diode or the junction, the doping of the two sites in A and NED, the temperature as usual, okay? What else? It has many things. Yes, the geometry, doping, yeah, and the material itself. Because we said there are many semiconductors. Carbon is a semiconductor. Germanium is a semiconductor. Silicon is a semiconductor. So, and all has, different, properties. All that will be reflected in I naught. And actually, I naught is equal to the area, which is the geometry, the cross-section area of the diode. let's draw it roughly here. So this is N, this is B. And this is the cross-section area. And basically, it's direct proportion. It has a direct relation, because basically, if you increase the area, you increase the current. You can absorb more charges. Multiplied by Q by N I square, and N I reflects the temperature and the material, because it's dependent on EG, and EG is different, which is the energy gap. It's different between material to another material. Multiplied by Dn, and also Dn reflects the material, over Na, the doping appears now, multiplied by something called Ln, I will explain in a moment, plus dB, and again the material, over Nd multiplied by Lb. Ln and Lb is something called diffusion length. And what's diffusion length? Basically, when a current flows, it may be not. So when a current flows like this, let's assume we have a battery like this. So maybe a current will flow and may make it to the wires and be absorbed in the battery. But it may recombine again, find some hole somewhere and recombine. So Ln and Lb is actually, we can say, the average diffusion length. If you have a diffusion, some of the electrons will not make it to the wires of the battery and recombine with holes before making it to the wires inside the diode. And the average length that they will move before making the recombination is called Ln or Lb. Ln is the diffusion length for electrons. Lb is diffusion length for holes. Okay, but we don't need any more details about this. But I'm just showing you that this equation has something very important called I naught, and I naught is actually the diode, reflects the characteristic of the geometry, doping, everything. Okay. What else we can see? Yeah, that's good. That's all for this I naught. Yes. Another also observation is the rate of change of ID versus VD. Okay. So let's have an example. And this is very important also. Let's assume IS or I naught, whatever you call it, 10 to the minus 6. And usually IS is very small, very, very, very small. Okay. And let's assume that I diode is equal to 1 milliampere. Find VD. Very, very basic example, simple example. We have our relation ID equal to I naught e to the power VD over VT minus 1. We know ID, we know I naught, we know VT, KT over Q, 26 millivolts, and one is constant. Okay, so let's simplify this. So I naught will be on the other side plus 1. So ID over I naught plus 1 equal to E VD over VT. Take len or logarithmic for both. So VD is equal to VT len. ID or len is a symbol for most of the people call it log, but I prefer to use log for base 10 or base 2, but I prefer to use len for the natural base of the natural number e over I naught minus or plus 1. And again here, this is dimensionless because what we take the length for should be dimensionless, and it's dimensionless. Ampere over ampere is just, you know, dimensionless, and 1 is dimensionless. And VT is V, so we are good. Just plug in the numbers. You know I naught, you know ID. So if we calculate this, VD will be equal to 778.27 millivolts. But B, again for the same problem, if ID increased 10 times, find Mr. VD. So now ID is equal to 10 milliamperes. What is VD? Again, we plug in the equation. We find that VD is equal to 838.14 millivolts. So very important observation, 2 observations here. So observation 1. ID changes very rapidly with very small increments in VD. And that's actually the relation, the exponential relation. If we draw this relation here, let's draw it, let's sketch it, let's plot it, and see. VD, ID, if you draw this equation, it will be something like this. You know, just put numbers for VD from minus infinity to infinity, just put numbers and plug in the equation and just get the ID and draw both together, point by point. You will find it's something like this. So let's, what we explained right now was all positive, right? ID was positive, VD was positive, right? So we are interested in that part here, in the positive part. If we look at this, you know, this part here, especially this part, you see, for very small change in VD, we have very big change in ID. Okay, that's good. So we expect, we can say that we expect that during, you know, operation, if the diode is conducting, the change in VD is very little, very small. Actually, in that case, it's a 7% increase. While the current of the diode will change, you know, will have a huge change, or, you know, flexibly changing, you can say. It's actually here 10 times. 10 times means 1000%. So this means 1000%. So for 7% increase in VD, ID increase 1000%. Or 10 times. Can we prove this in the opposite way? Yes. Just look at this equation in here. We can understand this relation, why for smaller change we have bigger change, 2 ways. Either by plotting ID or plotting the equation of VD, which we just derived from the original equation that we have. So let's draw it and see. Now, I will put ID on the x-axis. Let's go down here. And VD on the y-axis. And if we draw it, it will be something like this. And you see after some times, so this is exponential relation. This is now logarithmic relation. After some time, you know, VD is just like saturating, we can say. It doesn't increase so much. So as we increase the ID, the rate of increase of VD is decreasing. It's a little bit confusing, but you know, so if we increase ID, VD is increasing. But the rate of increase in VD is decreasing. So that, you know, you have this almost saturation shape. Here, no. So here, the rate of increasing VD is decreasing. That's why you have this kind of saturation. Here, the rate of increasing ID is increasing, actually. So this is the first observation, which is very nice. Okay. Now the second important observation. When ID equal to 10 milliamps, VD was around 800, we can say, something like this. You know, let's write it, 838 millivolt. And when ID is equal to 1 milliamps, VD was around 700 something, 768 millivolt. Let's look at these two numbers. We say that VBI or V naught, the built-in voltage, usually between 700 millivolt to 800 millivolt. And what are these values are telling us? They are telling us that when the diode operates or, you know, conducts, usually its voltage is very close to its VBI. It's a built-in voltage. It's a thing that is constant for any diode. Any diode comes with, you know, the built-in voltage. When you buy a diode, you know, if you look at the data sheet, VBI is equal to whatever. It will be something, for silicon, it will be something between 700 millivolt and 800 millivolt. So usually, okay, most of the time, the voltage that you see, the voltage drop off, or the, you know, the voltage drop across the diode when it operates or conducts is equal to its VBI. So VD usually approximately equal to VBI. This is one thing. VD usually doesn't change much. Very little change. Very little. This is the second important observation. Now, the third observation. It's also very important. It's regarding I naught actually. Okay. Or the relation between ID and I naught. Okay, that's fine. So assume this is another example. Assume VD is equal to minus 10 volt. Okay. Calculate ID. So ID equal to I naught E minus 10 over 26 millivolt, which is 0.026 minus 1. Now you have 1 minute. Okay, please calculate this value for me. You will get something strange. So if you get something weird or strange, just say it. That's fine.
-1.
Yes, that's right. Yeah. It should be -1. I'm sorry. If VD is negative and its value, but as a, the voltage value, I mean, is much, much, much larger than VT, E is minus to the power, it will be just like, VD over VT will be very large value, okay? So if we approximate it as infinity, for example, E to the power minus infinity is 0, okay? Of course, it's for your calculator, for example, E to the power minus 10 over 2.026 is, 0, 0, 0, 0, maybe, I don't know, 100 zeros, okay? That exceeds the length of your calculator, for example. So it's just giving you 0, okay? So with this observation here, this guy is -1. So ID is equal to I naught multiplied by -1 is equal to minus I naught. So I naught now has a meaning. Other than it's, it carries inside it, all the properties of the junction and, doping stuff, all such geometry, all such stuff. It's also the current that flows through the diode when the diode is reverse bias. Because you see here, the voltage is negative. That means the diode was reversed. You remember I said that when it's reversed, the current is 0 or almost 0? Yes, it's almost 0. Yes, we said that it's equal to minus I naught, but I naught usually very, very, very small. Like, for example, the first example here, it was 10 to the power minus 6. So for most of our application, I naught is really very small. Okay, and that's why when I draw the relation here, I made this. When the diode is in deep reverse, the current is actually equal to, let's make it with another color, minus I naught. In this region here, when you just substitute in the equation minus VD over VT, usually VD is in this region, VD is much larger than VT. So, and VD is negative, remember? So usually the calculator will give you just 0. So ID will be equal to minus I naught. But if VD is not that large, okay, you will have this part in here, which is also non-linear but also very small, because basically all these values is less than I naught as a magnitude. Okay, now we understand, you know, how things work. Now we have, our diode, our junction, which is governed by the famous equation. And let's draw it again just for your reference. So this is, here is positive, so this is forward, biased. And here in reverse, I am enlarging that width, although it's very small, just to make it noticeable for you. So in reverse, in deep reverse means VD is much, much, much larger than VT. We have a current of minus I naught. Okay, but if it's not that deep reverse, the current will, this term here will have a value, but in negative also, because E to minus something, it's less than 1. So for example, 0.5 for 0.5 minus 1 will be equal to minus 0.5. So still minus 0.5 I naught. So still negative, but not as much as I naught. Good. So in this reverse bias, this is reverse bias or reverse biased. Good. Now so this is what we know about the diode. We know now its equation, and we know some observations about our, diode now. So can we now play with it in circuits, put it with some other thing like a resistor and, voltage source and see what's happening? Yes, we can do, although it will be hard, but let's see. Oh, I'm sorry, just one, okay, before going to the example, just one final, observation, or, this is also physics. It's not final observation or something. Just before, yeah, let's go back here to this one. This is, yes, regarding I naught again, I said that, just one final remark about I naught. I said that I naught, now we have a definition for it. We know it. We know its physical meaning. It is the current that flows through the diode when the diode is reverse biased, deep reverse biased. Okay? So from where this current came from? There should be some carriers. And we said that the built-in voltage or the built-in potential, which will increase, by the way, when we apply reverse bias condition, will ban holes to move from the B type to N type, and also bans bans the electrons to move from the N type to B type. So from where is the carrier that do that? Actually, I know it is called the minority carrier current. This is, so I know this current here is minority carrier current. So this is B, this is N. Remember, we have here electrons, but they are minorities, right? And we have here electrons, I'm sorry, holes, but they are minority. So those guys can be, if you have a reverse bias, positive and negative okay? So those guys can be attracted to the negative terminal, and those guys can be attracted to the positive terminal. But since they are very small, a minority, okay, so this current is really, really small, which is I naught. So we now know its physical meaning, and we know from which it came from. It doesn't come from the majority carriers. It comes from the minority carriers. One last thing, I told you it's called saturation current. Why it's saturation? Again, because look at this curve, you know why it's saturation. So in reverse, the current develops in reverse direction, in negative, until some point, which is deep reverse, it saturates at one value, which is minus I naught. That's why they call it saturation reverse bias current or saturation current when it comes from the minority carriers. One last thing, and next time we will take examples, very nice examples. What's called diode breakdown, diode reverse breakdown. So basically from the name, it's a breakdown and it's in reverse. So till this moment, we learned that I naught equal to, ID equal to I naught exponential or E whatever, VD over VT minus 1. And if we draw this relation, ID, VD, it will be something like this. And this is minus I naught. Good. And we know that I naught is actually comes from when you have a reverse bias it comes from the B on that side, which is attracted to the negative terminal, and the N on that side, which is attracted to. If you increase the reverse voltage to a very high value, okay, remember this is, so now this minority current, which is I naught, those carriers are driven by or drifted, because this is a drift current, by VR. And remember, if you increase the voltage, you are increasing the mobility, right? I'm sorry, you are increasing, yes, you are increasing the velocity, the velocity of the carrier. And if you increase the velocity, if you go back to our previous lecture, you will find that the current is directly proportional to the velocity. So if you increase the velocity, you increase the current, because basically more charges are passing through the same time. So increase the current. So at some they found that at some value of VR, something called breakdown happens. So for all these values here, the current is minus I naught until some value called the breakdown voltage, a break happens. And the reverse current, exceeds minus I naught in the negative direction, of course. And at some point, the voltage across the junction will be equal to the breakdown voltage. This is called the breakdown voltage. And the current will change, rapidly like this, but in the negative direction. It can take any negative value smaller than, because we are comparing the negatives, smaller than minus I naught. For example, minus 2 I naught. Something small because of the negative, smaller than minus I naught. So at some value called breakdown voltage, some value of VR, you know, the velocity of the minority carriers increases so much. Okay, and one thing here is that yes, the velocity increases and this will increase the current, but also something, so this will increase the current, so this will increase the reverse current. But another phenomena also happens, that those carriers that are moving with velocity now has also a kind of momentum, a kind of energy, very high energy. So at the breakdown voltage, this energy is enough to say that if one of those particles or electrons or holes bombarded or hit an atom, a silicon atom, it can free some other electron. And those free electrons will also be accelerated, okay, using the VR and acquire some energy so that if they hit another atom, they free another electron and so on and so forth. That's why it's really very sharp increase in current, as you see here, very sharp. Because now it's not the minority carriers alone and their high velocity, no. It's also they generate those minority carriers hit other atoms and free other electrons or other charges. So those guys, this new generated atom electrons will also move very fast with high energy because we have the same condition, we have the same VR. So they will hit also other, you know, other atoms and so on and so forth. So that's why we also will increase not just the velocity of the carriers, but also their numbers. Okay. So the high energy minority carriers will have high energy enough to free other carriers. And you know carriers because if it hits an atom and it frees one electron, there will be a hole. So carriers from atoms they hit the new generated electrons or carriers, that's better. Carriers will acquire high energy from VR, and when they hit other atoms, they will free other carriers, and so on, so forth. Okay, guys? So that's basically all the physics or the conditions, okay, for the junction, for the diode. And next time we'll go to the, the most interesting stuff, which is basically the how to put them in a circuit and how we solve a circuit using with our new added device called the diode or junction. Okay.